Hi everybody! In this video we're going to explore experiments that you can do with the variable thickness muscovite sheet from Snellius Minerals. Here's an example of what these variable thickness muscovite sheets look like in ambient lighting. Our previous video looked at experiments that you could do with the oriented muscovite mica sheet from Snellius Minerals. And this item is very similar. What we've done here is we've taken one of those oriented muscovite mica sheets and we've removed different layers of muscovite mica to give us a variable thickness across the sheet. This is particularly good for helping us understand the generation of interference colors. We're going to focus on the generation of interference colors in this video. There's a whole bunch of background on muscovite mica in our previous video. Here's a link to Snellius Minerals oriented muscovite mica sheet. And to keep this video relatively short, we're gonna just go through the background information really quickly. Greater detail is available in that other video. And if you're interested in either the oriented muscovite mica sheet or the variable thickness muscovite sheet, you can find these at the eBay store, Snellius Minerals. There's a whole variety of other nerdy minerals with educational themes available too. In starting to talk about muscovite mica, we want to talk first of the big picture that's going on whenever we look at a mineral specimen. Our minerals are defined by their chemistry and structure. This in turn leads to the macroscopic crystallography and symmetry elements that we can observe, and also then the optical properties of our minerals. Our muscovite has a fairly complicated chemistry and structure. The chemistry consists of potassium, aluminum, silicon, oxygen, and hydroxide, and the structure is that of a TOT dioctahedral sheet silicate with interlayer potassium. Here is a greatly simplified structure model for our muscovite. There are two important pieces of information that go along with this structure model. The first is that the space group of our muscovite is going to be C2/C. This means our muscovite is going to be monoclinic. And the second is that the bonding within our TOT structural layers is actually going to be stronger than the potassium bonding that bonds those layers together. As such, our muscovite has perfect cleavage, and this cleavage plane only cuts the C crystallographic axis. Back out to the big picture, we talked about the chemistry and structure that define our muscovite, and the perfect cleavage that cuts only the C crystallographic axis allows us to make such nice sheets of muscovite mica. The perfect cleavage is also one of our main clues of crystallographic orientation. When looking down onto one of these flat sheets of muscovite mica, we are looking down onto the plane of the A and B crystallographic axes. However, we don't exactly know where the A and B crystallographic axes actually lie in this plane. We'll need more information in order to figure that out. But we do know that our C crystallographic axis will be perpendicular to our B axis and at an angle of 95.5 degrees to the A crystallographic axis. We've covered the chemistry and structure of our muscovite, as well as how the cleavage plane in our muscovite gives us a sense of crystallographic direction. We'll now investigate the optics of our muscovite, and in order to do that, we want to think about the optical indicatrix for our muscovite. This is a three-dimensional representation of the refractive indices of our substance. And in the case of our biaxial muscovite, the shape is a triaxial ellipsoid. In many of the more symmetric crystal systems, the axes of our optical indicatrix and our crystallographic axes align. However, because muscovite is monoclinic, only one of our crystallographic axes and the axes of our optical indicatrix will. The B crystallographic axis of our muscovite aligns with the Z direction of our optical indicatrix. Our C crystallographic axis is inclined anywhere from 0 to 5 degrees to the X direction of our optical indicatrix, and our A crystallographic axis is inclined anywhere from 1 to 3 degrees with respect to our Y direction through our optical indicatrix. We know from earlier that the cleavage of our muscovite only cuts the C crystallographic axis, and so when looking onto one of these cleavage surfaces, the view of our optical indicatrix that is closest to what we'll actually see is this one. We'll focus on this view now, but do note that we're 1 to 3 degrees away from where we should be. So technically the view we'd actually have of our optical indicatrix is a bit more like this. You can think of this as a rotation of the optical indicatrix by 1 to 3 degrees, depending upon that angle between our A crystallographic axis and the Y direction of our optical indicatrix. The shape of our optical indicatrix in this view has changed ever so slightly as well. Instead of refractive index beta, here we have refractive index alpha prime, which is a value somewhere between refractive indices alpha and beta. As we've only rotated the optical indicatrix between 1 and 3 degrees, this value of alpha prime is going to be very, very close to beta. Let's also take into consideration where our optic axes will be in this diagram, here represented by 2 stars, and further note that the interference figure that we generate with this view of our optical indicatrix is almost an acute bisectrix figure, or a BXA figure. Once again, we're 1 to 3 degrees away from this view, just depending on how far we've actually rotated our optical indicatrix. Now let's put our theoretical knowledge into practice by taking a look at our variable thickness muscovite sheet with a polariscope. We are currently viewing our variable thickness muscovite sheet in plane polarized light, and the vibrational direction of our light in this image is in a north-south direction. We'll now bring in our upper polarizer so we can view our sheet with crossed polarizers. And the variety of different colors that we're seeing in this view are interference colors for our muscovite mica. Our muscovite mica is an anisotropic substance with respect to light. So in many orientations, when our plane polarized light enters our muscovite mica, it's going to be split into 2 beams that vibrate in mutually perpendicular directions. These 2 beams are associated with different refractive indices as they travel through our crystal, and so travel through our crystal at different speeds. That difference in speed of our light rays as they travel through our crystal ultimately gives rise to our interference color. Before we delve a bit deeper into that topic, let's actually generate an interference figure for our mica sheet so we can get an idea of its orientation. To do this with our current polariscope setup, we'll bring in a converging lens, and we can see here our almost BXA interference figure. With the combination of the knowledge that we're looking down on the cleavage plane of our muscovite mica and the location of the melitopes in this interference figure, we have enough information to fully understand the crystallographic orientation of our muscovite crystal. And for a more detailed dive into this, check out the video Snellius Minerals Oriented Muscovite Mica Sheet. Now let's focus on the refractive indices of our muscovite mica that we'd see in this view. We'll go back out to our appropriate view of our optical indicatrix. While our optical indicatrix is 3-dimensional, for a single view through our mineral of interest, we only actually have to think about a plane through our optical indicatrix, in this case the gamma alpha prime plane. Let's go back out to our view of our variable thickness muscovite sheet in plane polarized light. And now we have some handy diagrams about refractive indices to help us think about what's going on here in the generation of an interference color. Our plane polarized light in this view is vibrating in a north-south direction. When it interacts with our muscovite crystal, it's going to split into 2 beams that vibrate in mutually perpendicular directions associated with refractive index gamma and refractive index alpha prime. These 2 beams are going to travel through our crystal at different speeds. And so the difference between their travel time through the crystal is going to be based on the difference in refractive indices, also known as the birefringence, as well as the thickness of our sample. The interference color that we see when we bring in our upper polarizer is a result of the difference in travel time of our 2 rays. This difference is also known as the path difference, or also a retardation. Let's now switch over to a bit more mathematical treatment of what's going on here. Conceptually, our interference color is going to be based on the thickness of our sample and the birefringence of our sample in this particular view. So delta, which is the path difference, is equal to d, the thickness of our sample, multiplied by N2 minus N1, which is our birefringence, the difference in refractive indices. For this equation, if we know any two of the three variables, we can of course solve for the third. Right now, the one variable we know for sure is the birefringence of our muscovite mica in this view. So in this equation, we can replace N2 minus N1 with gamma minus alpha prime for our muscovite mica. The refractive indices of our muscovite mica do have some variability given limited solid solution substitutions occurring within muscovite. However, for today, for simplicity, we're going to use 1.599 and 1.590 for refractive index gamma and alpha prime respectively. The difference between gamma and alpha prime is then 0.009, but we'll need another variable in order to be able to use this equation. And I don't have any information on the thickness of this sample yet, but what we do have are our interference colors. Using our interference colors and a tool known as the Michel-Levy color chart, we can calculate the path difference associated with each of our interference colors. Thank you also to Zeiss for allowing me to use their very nice Michel-Levy color chart. There are a variety of ways to use the Michel-Levy color chart, in particular with thin sections, but we're actually going to do something fairly simple today. We have our interference colors for our muscovite, and all we're going to need to do is spot the appropriate colors on the color chart. There is a bit of complication here as we have different orders of colors, and as the order of the color increases, it gets sort of more and more pastel and washed out. It does take a bit of practice to use this tool appropriately. Now let's give it a try with our variable thickness muscovite mica sheet. We'll zoom in on a section of the Michel-Levy color chart, and now let's add in an overlay of the interference colors that we have with our muscovite mica sheet. This image of our muscovite interference colors has been rotated and cropped, but that is indeed the same muscovite mica sheet. We can now spot where our interference colors for our muscovite mica sheet actually line up on the color chart. And on the bottom of the chart, we can read off a value for the path difference that each interference color is associated with. For this particular variable thickness muscovite mica sheet, I chose the values of 664 nanometers, 910 nanometers, and 1101 nanometers for our path differences for our different interference colors. And with those pieces of information, we can now calculate the thickness of each section of our muscovite mica sheet using the interference colors and the birefringence of our muscovite mica. The section of our muscovite mica that has a light blue interference color suggests that section is around 74,000 nanometers in thickness. The section with a yellow interference color is somewhere around 101,000 nanometers in thickness. And the section with a magenta interference color is around 122,000 nanometers in thickness. Here's a summary of those results for this particular variable thickness muscovite mica sheet. With our nanometers converted to micrometers, a micrometer is 1,000 nanometers. And if you purchase one of your own variable thickness muscovite mica sheets to try these experiments out at home, your results will be different as all of these are unique. One last piece of new material before we review everything that we've done today. I just wanted to show off how the interference figure for our muscovite mica changes with the thickness of our muscovite sample. Pay attention to where the interference color that we see in each section of our muscovite sheet ends up in our interference figure for that section. We'll leave a more in-depth treatment of this topic for a different time. Today, we took a look at the variable thickness muscovite sheet and some of the fun experiments that you can do with this sheet. We first reviewed some of the properties of our muscovite mica by taking a look at a simplified structure model of our muscovite. We then looked at our variable thickness muscovite sheet and how the cleavage of our muscovite can help us orient it crystallographically. We then reviewed the optics for our muscovite by looking at the optical indicatrix, a three-dimensional representation of the refractive indices of our muscovite. Our muscovite is monoclinic, which means that our crystallographic axes and the axes of our optical indicatrix are not fully aligned. Given that our muscovite is lying on a cleavage surface, we then figured out what view of our optical indicatrix we would be seeing in this orientation. By combining our understanding of the optical indicatrix of our muscovite in this orientation and the interference figure that muscovite generates, we can fully understand the crystallographic orientation of the muscovite in this view. From there, we talked about how plane polarized light interacts with our muscovite crystal. Our anisotropic muscovite causes the plane polarized light to split into two beams that vibrate in mutually perpendicular directions. In this particular case, one of those beams is associated with refractive index alpha prime and the other associated with refractive index gamma. Those two beams travel through our crystal at different rates, and this path difference is what we see as an interference color when we bring in our upper polarizer. The interference color that we see is associated with the difference in refractive indices of our substance in this particular view, known as the birefringence, and also the thickness of our sample. Here's that conceptual statement expressed mathematically. Delta, the path difference, equals d, the thickness of our sample, times n2 minus n1. Those are the refractive indices of our sample, and their difference is the birefringence. We know what N2 and N1 are for our muscovite in this orientation. N2 is going to be refractive index gamma, and N1 is going to be refractive index alpha prime. The birefringence will be 0.009. We still need another piece of information in order to use this formula, and what we did next was figure out how we can use our interference color to calculate the path difference using a Michel-Levy color chart. Our three different interference colors of our variable thickness muscovite sheet align with path differences of 664 nanometers, 910 nanometers, and 1101 nanometers. Using our formula, we can then calculate the thickness of each section of our muscovite sheet. And that was our main goal for today, was to use our variable thickness muscovite sheet in order to learn a bit more about interference colors. If you'd like to try out these experiments on your own, you can pick up a variable thickness muscovite sheet from the eBay store Snellius Minerals. And if you have any thoughts for me about these videos or any other minerals you'd like me to investigate, feel free to email at snelliusminerals@gmail.com. Here are the references I used in the construction of today's video. Our next video will also involve muscovite mica, and will explore constructive and destructive interference. Thanks again for watching, and have a great day!